Alright, this is 7.3 notes for Precalculus, because Kramer's rule. There is another way to solve linear systems using inverses. And then later on we'll talk about Kramer's rule, which involves determinants. So suppose that a linear system of equations has a matrix A and a matrix X. The matrix X is a set of variables, and then it's equal to a matrix B, which is a matrix of constants. What I mean is that we have a simple equation, AX equals B. So suppose that we came up with just a small example, say 2x plus 3y equals 4, and negative 5x minus y equals 8. Just any numbers you want. Well, I could write this in matrix language. There's a matrix of coefficients. There's a matrix of variables. And there's a matrix of constants. What we're used to seeing is if we put those two together, that would be an augmented matrix. But just notice that if we make simply the coefficients, that's a square matrix. The other thing that we can note is if you multiplied the matrix A times X, you would end up with the original set of equations. So write the following system of equations in the form AX equals B. Just take note that that last equation there doesn't have the constant by itself. We need to solve for it. Now we can use these three equations. Here are my variables in the system. And then here's a matrix of constants. It might be a little bit confusing that our matrix equation has an x in it as well as one of the variables, but just notice that this is going to be all capital letters. Now, if A is invertible, and we're talking about square matrices here, then the solutions to X is given by here's our equation. Now what happens if I were to multiply both sides by A inverse? Those two matrices multiplied together will give us the identity matrix. But please, please, please make sure that you absolutely must write A inverse on the left side, because order of the multiplication matters a great deal. So you have to write this on the left side. The identity matrix multiplied with x will just yield the x matrix. So finally we have this. Okay? Once again, remember that A inverse AX is not equal to B A inverse. No good. Here's our example. Solve the system of equations using invertible matrices, not Gauss-Jordan elimination. Well, we know that AX equals B, and also that X is equal to A inverse B. Our first step should be to get the inverse. So A is equal to now I'm going to set up the identity matrix here to get me that inverse. So let's multiply by 1/2 on the first row. Then let's multiply 3 times R1 plus R2. Next, let's multiply row 2 by -2/5. Almost there. Let's multiply -3/2 times R2 and add it with R1. So the first part of the problem is to find the inverse, which we've done. This next part would be to multiply A inverse times the matrix of the constants, -25 and 60. Let's see what that looks like. So 7/5, this is row times column, times -25, plus 3/5 times 60. And then the next one, row times column, Once we put that together, that should give us a matrix that is -25, +60, which tells us that x is equal to, not -25 and 60. We put all those together, we should get 1 and 9. That makes a lot more sense. So x is 1, and y is -9. And we're done. So this is now a way to solve a system using inverses and a matrix equation. Please make sure to comment on this video for credit, and then have a nice day.